The Earth may seem like a stable, static hunk of matter. When considered on the scale of any of our lives, or when viewed from one day to the next, it doesn't change much. However, the Earth is approximately 4.5 billion years old, and is part of a universe that is nearly 14 billion years old. So it exists on an entirely different scale of time than either you or I can easily comprehend. Over those 4.5 billion years, it has actually changed significantly, mostly through processes that you've already heard of. Processes inform events such as astronomical events, plate tectonics, weathering and erosion, and atmospheric gas exchange and movement. These same processes have been working since Earth was just a molten ball without an atmosphere or any liquid water to speak of, and continue through today. Sudden changes do take place after catastrophes, but they only increase the rate at which the Earth changes. This theory that the same processes that shaped and changed the Earth in the past continue today is called uniformitarianism. Though we may not always notice it, evidence of how the Earth has changed exists all around us, primarily in the rock beneath our feet. The people who study the Earth and the history stored in its rock are called geologists. People who specifically study past life through such methods are called paleontologists. Whether studying the history of the Earth or the history of life upon it, one of the most important pieces of information to determine is the age of the rock under investigation. Geologists use two methods to do this. First gives a relative age and is based on the layering of sedimentary rock, and the other gives a more exact estimate based on the radioactive decay of isotopes in the rock. The first relies on the seemingly common sense way in which erosion and deposition work. After rock erodes, it is deposited somewhere else. When it is deposited, it settles on top of whatever earth was already there, meaning that newer deposits are usually above older ones. Anything found in that layer is probably the same age. As a result, by looking at how rock is layered, one can determine how old a particular layer or something in a particular layer is relative to the other layers. This principle that younger deposits of rock lie above older deposits is called superposition. The continuous change of Earth's surface can disrupt these layers, causing unconformities, but since anything found in a particular layer is probably from that same period, it is a good place to start the dating process. A more precise method for determining the age of geologic evidence is called radiometric dating, which dates particular evidence by measuring radioactive isotopes. Isotopes are the different versions that the atoms of a particular element can have, each with a different number of neutrons, and resultantly a different mass number. Some versions, some isotopes, are unstable and tend to decay or break down over time, turning from a term called the parent isotope into a simpler form called a daughter isotope. Different isotopes decay at different rates, but each has a particular rate at which it decays. If scientists can determine the ratio of parent to daughter isotopes present in a sample of rock, and if they know the rate at which it decays, they can determine how long it has been decaying and thus how old the rock is. Some isotopes take hundreds of millions of years to decay, and others take only a few thousand years. So scientists have to decide what element isotopes to measure when beginning this process. Looking at superpositioning first to determine the relative age makes this much easier. One example of a radioactive isotope used for radiometric dating is carbon-14. This is an isotope of the element carbon that has 8 neutrons, compared to the majority of carbon atoms that only have 6 neutrons. Carbon-14 is unstable and decays over time. After 5,730 years, half the carbon-14 in a sample will have decayed into a simpler and more stable form, nitrogen-14. Knowing this rate and the amount of parent isotope, carbon-14, and daughter isotope, nitrogen-14, allows scientists to determine how long they have been decaying and thus how old the sample is. This particular isotope has a relatively short half-life, so it can't be used on samples of rock or artifacts that are older than about 60,000 years. Some isotopes, though, take billions of years to decay, so there are radiometric dating procedures available to determine the age of much older samples. One of the most interesting ways scientists use radiometric dating is to determine the age of fossils, which are the remains of ancient organisms usually preserved in sedimentary rock. The most well-organized kind of fossils form when minerals fill the empty spaces in an animal's skeleton and eventually replace its skeleton with rock. The dinosaurs that are on display at natural history museums around the world are fossilized in this way. Some animals, though, are fossilized when they are trapped in amber, tar, or ice. Occasionally, animals preserved in these ways are so well isolated from the elements and decomposed organisms that even their soft tissue, such as muscle or hair, is protected. Other kinds of fossils aren't actually organisms at all, but evidence of their presence, such as footprints, imprints, or nests. These fossils are called trace fossils. Fossilization of any form only occurs when an organism or trace evidence of an organism is buried or removed from the elements immediately after dying. Few of the countless things that have lived on Earth actually remain as fossils for us to investigate now. Studying the fossil record is one of the best ways to learn about Earth's past. However, there has only been life on Earth for about half of Earth's history, and there was little life more complex than bacteria until about 540 million years ago. So even the fossil record leaves out a large portion of Earth's history. Human written history only accounts for about 0.000109% of Earth's actual history. The word history actually refers to a written record of time, so very little of Earth's past is actually part of history. Since Earth is so old, we have to break its past into larger segments of time than days, months, years, decades, centuries, or even millennia. Instead, we use the geologic timescale, which divides the time the Earth has existed into eons, eras, periods, and epochs. These divisions are not based on a standard amount of time like days or years, though. Alternatively, these divisions are based on significant geologic changes to Earth or to the organisms living on it, such as the first rocks appearing, the first living things appearing, the first complex life, or a mass extinction. If you look at the tables, you may recognize the names of some of the eons, eras, periods, or epochs. The names are usually either descriptive of the period and its position on the geologic timescale, or rooted in the location where most of the fossils dating to that time period were found. You don't need to memorize these specific eons, eras, and periods and epochs, but you should know that eons are broken down into smaller eras, that eras are broken down into smaller periods, and that periods are broken down into even smaller epochs.